The next thing we're looking at is concavity, how a graph bends. We call something concave up, like that. Think of a smiley face. Things are looking up, right? It's almost Monday. Which in the new outlook of life is always positive. So it's good. There's our concave up. And if you draw any tangents on there, the graph is always above the tangent. That's what makes something curved that way, related to its tangents. Similarly, right? So here's examples of all the tangents. And if you look at the second derivative, if a derivative is a rate of change, how fast something is changing, what its slopes are. The second derivative is the rate of change of the first derivative. The second derivative is finding out how fast the first derivative is changing. So if your second derivative is positive, that would mean, just like we did before with the number line, positive on a derivative means the function above it was increasing. So positive on the second derivative means your first derivative is increasing. If your first derivative is increasing, see how these slopes go from 0.24 to bigger, 1.07, to bigger, 4.05. All of these concave up ones, here the slope is negative, then it's 0, then it's positive. All of those tangents are increasing. Anytime tangents are increasing, you will get your curve being concave up. So our first derivative we will use to say our original equation is increasing or decreasing. Our second derivative will be able to say whether it's concave up or concave down. And if your second derivative is positive, so we will now have a positive outlook on life and get a smiley face, that'll be concave up. Oh, we're going to end on a negative. Shoot. Could have done a little bit better planning here. Concave down. Oh. If all of your tangents, which no matter where I draw a tangent on a concave down, make a mustache, whatever, the tangents would be above the graph. The tangents number, the slope would be decreasing. So if you want something to be decreasing, the derivative would have to be negative. So a negative second derivative means that the first derivative is decreasing. And a negative second derivative will mean that the original function is concave down. So we will now have a number line where if we get a negative, we'll draw a negative cyclops sad face. Just show that it's concave down. So on our next question, there it is. I'm going to do concave up in green, then concave down in red. So we have the points P and Q and R, and those are points where the graph changes concavity. So can you see that this part up to P is all concave up? Then it switches to concave down, switches back to concave up, still is concave up here, and then goes back to concave down. And we call the places where a graph changes from concave up to concave down as points of inflection. We've learned that word or seen that word already because we had stationary points of inflection with an x cubed graph. On your x cubed graph, at that point, do you see that it changed from concave down to concave up? But it also happens to be that the tangent was flat. On most inflection points, like if I drew a tangent at point P here, it doesn't have, it's not stationary. Only on x cubed graphs and similar things like that, you have stationary points of inflection. Most points of inflection just change from concave down to concave up or concave up to concave down. And they will be another point that helps us graph things really easily. So we'll have our maximums and our minimums. We'll add our inflection points. And in order to say that something's an inflection point, you have to show two things. You have to show the second derivative is 0, and you need to show that the second derivative changes sign. It's not enough just to say it changes sign, and it's not enough just to say that it equals 0. Here's another mathematical word for you. That's called the cusp. It would be at a non-permissible value. Because at that non-permissible value, there would be no, like at a sharp point like that, there's no derivative, because you could draw multiple tangents. It'd be like a non-permissible value for your derivative. Sometimes you have non-permissible values in your derivative that you didn't have in your original equation. So those are inflection points and concavity. Yeah, we can do one more thing in notes. So stationary points of inflection. In order to have a stationary point of inflection, you could show that the first derivative is equal to 0, because that gives you a stationary point. And you can show that the second derivative is equal to 0 at that point. So both the first derivative and the second derivative are equal to 0 at the same point. Most likely have a stationary point of inflection, but you still need to show that it changes from concave up to concave down. Okay? Or you could show that the first derivative, if it keeps increasing, you would have, so this is what you have. Your first derivative and second derivative are equal to 0 at this point. If with your first derivative test, let's call this point C, it says increasing, increasing, well, then this has to happen. Or if at that point C, you have concave down, concave up, yeah. Those are good sound effects. Then point C is an inflection point. And if your first derivative is 0 and you have an inflection point, it can't be like there is no way that you can draw a maximum and change concavity at a maximum. You can't have it bent one way and bent the other way and still have it a maximum or a minimum. So if you show either of those two things, you will show that you have a stationary point of inflection. For your non-stationary point of inflection, that would mean that your derivative isn't 0 at that point, but your second derivative is, and your second derivative still changes sign. So if I had, if I have an execute graph like this, you will have a non-stationary point of inflection right there, right sort of in the middle. You can see it changes from concave up to concave down. At that point, it's not a max or a min. So your first derivative will not equal 0. You can see if I drew a tangent there, looks like my first derivative would be a positive slope. Okay? But it does change from concave up to concave down at that point. So again, similar to what we said about the first derivative test, for inflection points, it is not sufficient just to show the second derivative is 0. You also have to show that either the first derivative doesn't change sign at that point, or more commonly, something that you are going to have a misconception with later on. To find points, inflection points, we use the second derivative. But this is not the second derivative test. But because you use the second derivative, your brain will start to think it is. That's what second derivative test, I'll find my inflection points. We will find out later what the second derivative test is, but this is not the second derivative test. Okay, we'll end there.